Okay, so today we are going to talk about environmental conditions. Um, so we're going to cover heat, altitude, and cold. Starting with heat, we're going to cover the physics of heat transfer, some acclimatization timelines, how you can pre-acclimatize to if you know you're going to be competing in a hot environment or performing physical activity in a hot environment, how that affects potentially cold weather. Performance, and then some hydration and strategy uh, recommendations. So first of all, right, contraction of muscle produces heat. So about 80% of caloric consumption is due to heat loss, or rather 80% of energy production is lost to heat. And so if I expend 134 calories to run a mile, that's somebody of my size, right? So it's body weight specific. But if somebody of my size runs a mile, it requires about 134 calories. And about 107 of those calories are lost as heat. And the definition of a calorie is that it raises 1 kilogram of water by 1 degree Celsius. Then if we account for the fact that humans are about 50 to 60% water, right, running a mile should increase my body temperature by about 45 degrees Celsius, but it doesn't. And we see that over here in this figure on the right. This was looking at 8 cyclists who were asked to complete as much work as they could in 60 minutes, right? So they're still working hard up here, but body temperature does sort of level out. Instead of increasing by 45 degrees Celsius, we see it increase by maybe as much as 2 degrees Celsius. Okay. So what is happening? So we see most of the heat is being generated, right, by that caloric consumption and just muscle contraction, right? But we also see some additional heat generation from solar radiation, right? If you're working out in a sunny environment, or from ground thermal radiation as well. So particularly if I had an athlete who was working out on some type of turf, especially if it was really reflective, light in color, right? That's going to contribute to increased core body temperature. And the primary way in which we lose or in which we reduce core body temperature is through evaporation. A little bit through respiratory evaporation, primarily through sweating, though. So evaporation of 1 liter of water dissipates about 580 calories, which is equivalent to about 4 miles of running. So if I can lose a liter of water in a 4 mile run, I should be able to maintain roughly my same core body temperature. In order to do that, I have to increase skin blood flow, right? Simultaneously, while I need to increase skin blood flow, I'm losing plasma volume, which is just essentially a surrogate for the amount of water or fluid in my blood, right? So my blood is made up of cells, right? But there is fluid in there as well. And so that's the difference really between blood and plasma, right? We sort of see them as the same homogeneous fluid, right? But when you centrifuge them, you see sort of plasma differentiate between or from the red blood cells, okay? So our blood is about 55% plasma. So if we see reduced plasma volume, right, then that makes my blood a little bit thicker, which means that I'm going to decrease my stroke volume, increase my heart rate in order to maintain that blood flow to the skin so that I can keep trying to reduce core body temperature. If I'm not able to do that, I have hyperthermia. So metabolic heat leads to excess heat loss, metabolic heat exceeds heat loss rather. Right. So my core body temperature is increasing. So when I'm exposed to heat, right, so that's what happens acutely when I'm exposed to heat, right? An increase in heart rate, decrease in stroke volume, increase in skin blood flow. Okay, but what happens when I'm chronically exposed to heat? So across the course of about 7 days, I see an increase in plasma volume of about 10%, maybe up as high as 15%. Okay. Simultaneously, right, I've then now decreased the work on my heart, right? So my heart rate can drop back down to maybe more baseline levels, about 80 beats per minute, as opposed to that initial exposure to heat. I might be doing the same amount of work at about 100 beats per minute. Okay, we also see a couple of other adaptations, right? My skin temperature over time does seem to reduce. I've also got reduced core body temperature. I've got improved sweat rate and improved work capacity, right? So as sweat rate increases, as plasma volume increases, heart rate decreases, I'm able to perform more work. Okay. Also, what I think is interesting too is we talk about thermal comfort. So this is just how comfortable these athletes were. And you see that comfort does sort of peak at around day 6 or 7, similar to where plasma volume and heart rate do. So oftentimes when someone feels uncomfortable, it's the result of these sort of physiologic processes that are happening. So we start to feel better as soon as our body has had time to adapt. Um, if you know that you are going to perform in a hot environment, or if you are coaching and you have athletes who are going to be working in hot environments, what can you do to pre-acclimatize them or to prepare them for that? This was a study that showed that you could increase blood plasma volume with exposure to a sauna. And in some individuals, they were able to increase it by as much as about 18%. You can see, right, pretty big confidence intervals here. So maybe my average is more around 10%. But in any case, it appears that sauna exposure does increase blood plasma volume. Okay, and that may be one reason why we see improved cardiovascular health with sauna exposure as well. And then another study examined hot water immersion. So this is just hot tub exposure, and we see when we compare, uh, let's use the performance measures. It's a little easier to make that comparison. But when we compare performing in a cool environment to performing in a hot environment, so 18 degrees Celsius is about 64 degrees Fahrenheit, 33 is about 92 degrees Fahrenheit. And we see that in hot environments, right, the time to complete a 5K goes up, right? It takes me longer because I'm having to work harder, right? Um, what we also see though is that in whether I'm in the cool group or in the hot group, right, that exposure to that hot tub does seem to decrease time and significantly so in that hot group, especially. Okay. The reason I included this figure is because it's what's called a spaghetti plot. So these individual lines represent individual athletes. And we can see, so in this first, in the hot water group that was exercising in a more temperate environment, we still saw improvements in core temperature, right? Uh, However, and this is pretty homogeneous. However, when we come over here in the control group, right, now I see some individuals are sort of straight across, no real significant difference here. But so this athlete, right, had actually an increase in core temperature. This athlete had a pretty significant decrease in core temperature, and most athletes are sort of straight across. So sometimes spaghetti plots are just kind of cool because they let us look at individual response instead of just looking at the mean response in the group. Okay, I'm not going to go through each one of these, but this was a pretty cool study that had cyclists perform sub-maximal work, right? So they're not getting up to max, and it looked at changes with acclimatization, right? So going through that 7 to 12 days of acclimating to the heat, and then also with cool or hot environment performance. And they looked at several different measures. So they looked at VO2 max, they looked at total work performed, lactate threshold. So we think that, right, we would expect that VO2 max does, in fact, increase in the cooler environments. It increases with acclimatization. And one of the reasons that we think that might be happening is that these changes in lactate threshold, right, in cardiac output and in stroke volume. Okay, so because that, right, that plasma volume is increasing, I would expect that, yes, indeed, in the acclimatized group, my plasma volume is significantly higher, and it's significantly higher in the cool group compared to the hot group. Okay, so I'd love if you would pause the video and sort of go through these and see if you can identify the patterns that are occurring here. Where I want to provide some hydration recommendations. This comes primarily from your text, but I wanted to go over them really quickly. So 4 hours prior to engaging in exercise, I would recommend, or rather ACSM recommends, zero point 0.1 ounces times your weight in pounds. So for someone my size, I'd be looking at about 16, 17 ounces of fluid here. If 2 hours before an event, I haven't urinated or my urine is really dark, they would recommend half that amount once again. So for me, about 8 ounces of additional fluid 2 hours prior to an event. To rehydrate post-event, they recommend a half a liter per pound of body weight loss. That assumes that you have weighed prior to exercise and then weigh right after exercise. This is always done, if you want to be scientific about it, it's done in the nude, right? Because I want to acknowledge how much body weight or how much water my body has lost, right? But if the water is still stuck to my clothes to any extent, right, I'm still measuring that weight. Okay, so you would want to do this in the nude if you were going to do this. Um, that hydration fluid, though, so that's about 17 ounces per pound of body weight loss, should also be about 20 to 30 molar equivalent units per liter. What that means is that I need some amount of sodium, potassium, and carbohydrate in that fluid as well. So for someone my size, I'd be looking at 460 to 690 milligrams of sodium in that 17 ounces. I'd be looking at 78 to 195 milligrams of potassium and then 17 to 35 grams of carbohydrate. Now I want to come over here and take a look at these two beverages. So we're going to start with this one on the right. This is, right, it's a 12-ounce beverage. Okay. So, or sorry, it's 12 ounces per serving, and this is 2.5 servings. Okay. So I'm looking at about 30 ounces here. So if I had lost about 2 pounds, then this amount of fluid is what would be recommended. Now we want to see, okay, am I hitting the recommended amounts in terms of the sodium, potassium, and carbohydrate? So here we've got 440 milligrams, right? We can see that's a little bit low. If I look at carbohydrates, 58 grams versus 17 to 35, a little bit high on the carbohydrates. Um, and then down at the potassium, I've got 120 milligrams, pretty squarely right in that recommended amount. So uh, pretty decent beverage here. Maybe could decrease my carbohydrate a bit. Then we've got this other beverage. And the only real difference is that this beverage includes some protein. Okay, so this is intended to be a recovery beverage. And I include this partly because we've talked about that ratio of carbohydrate to protein that would be advantageous for recovery to exercise. And in aerobic performance in particular, we talked about having greater than a 1-to-1 ratio. And here we see we've got about a 2.5 grams of carbohydrate per gram of protein. Okay, so again, sort of fitting inside that recommendation. And these are beverages produced by Gatorade, and they do try to be pretty science driven. So just interesting to sort of take a look at that. The Galpin equation is something that Andy Galpin has used in the past. So it's just a way to helpfully think about the amount of liquid to rehydrate with as well. So you could take your body weight in pounds, divide it by 30, and use that every 20 minutes during exercise that's going to last longer than 60 minutes. Okay, so, and I might want to consume that every 60 to 90 minutes is his recommendation. Then post-exercise, just resuming normal consumption usually results in what we would call a euhydrated status, meaning I'm not dehydrated, right? Plasma volume is healthy. If you need to rehydrate quickly, let's say you have performance later in the day, so you perform in the morning and then perform again in the afternoon, consuming 23 ounces per pound of body weight lost, in addition to that, these sodium, potassium, and carbohydrate recommendations is what would be recommended. Okay, and then I just like to present some actual data here. So when we look at core body temperature, this was a Gatorade trial. When we look at core body temperature, they looked at a water plus carbohydrate, so Gatorade, a water, just carbohydrate ingestion, and then a placebo group. And you can see that with core body temperature, we saw the greatest increase in the carbohydrate group, right? They're having to digest that carbohydrate, so they're losing a little bit of water there. In the control group, right, we saw significant increase in core body temperature and then significantly less increase in both of the fluid groups. So not much difference between water and carbohydrate here. And then we look at maximal performance, so my ability to maintain work across that same time frame. And what we see here is, right, is that water and carbohydrate group was the most capable of maintaining high performance. Water group seemed to do pretty well as well, but that carbohydrate and placebo group both were not able to maintain power across time. These are some interesting statistics down here as well. So if we're looking at a decline in blood volume, we had large fluid group and small fluid group, right? And if we compare that to the decline in plasma volume, right? Large fluid group and small fluid group, we see about double the amount of plasma volume reduction in the small fluid group as compared to the large fluid group. So I just wanted you to see that this does actually play out in research and it's not just me talking. Another interesting study here. So this was looking at unacclimatized and heat acclimatized individuals. That's the UA and the HA. And then hypohydrated, meaning dehydrated individuals, and then euhydrated groups. So we can tell pretty clearly, right? Hypohydrated, so dehydrated individuals had these significant increases in core body temperature as compared to the euhydrated group. And in the euhydrated group, so let's assume that you are indeed hydrated appropriately, that acclimatized group does indeed maintain a lower core body temperature than the unacclimatized group. So one thing in terms of performance strategy, right, I would want to be hydrated and I would want to be heat acclimatized. Another thing that I can do is called pre-cooling. So we've got a couple different strategies here, but a cooling vest, water immersion, slushy ingestion, so like icy water, cooling packs, mixed methods of cooling. And in any case, cooling prior to an event does seem to have a significant effect on performance and does indeed improve performance. This is another sort of pre-cooling, or this would be more maybe pre-cooling as well. So ice vests, cold water ingestion, and cooling packs did seem to significantly improve performance in a hot environment. Particularly those ice vests had a massive improvement, huge confidence interval though, right? Partly because there's so few individuals included in the study. Okay, so the last thing I'm going to introduce in terms of heat, and then we'll give you a little break, is this wet bulb globe temperature. So this takes into account temperature and humidity, right? So we know that both temperature and humidity would affect the rate at which the sweat is going to evaporate, which then affects my cooling. Because at a certain point, it might be so humid, right, that the sweat that I'm producing is actually not evaporating because the air is so humid. So high humidity would be a problem, and high heat would also be a problem. So if we look right somewhere in the middle, we're looking at like exercising in 93 to 96 degrees. I will ask you a question about this on your pre-class or post-class engagement, just for the head as a heads up. If I drop down to, let's say, a humidity of 40% and I'm exercising in like a 93-degree Fahrenheit weather, this is kind of a danger zone, right? So my wet bulb globe temperature here would be 87.8, although my ambient air temperature is 93.2, okay? We're in a dangerous spot here. So um, this figure correlates with this figure, right? So if I'm in that 87.8, so that 93 degrees Fahrenheit and that 40% humidity, right? That's going to say that my heat risk category is high for unacclimated and acclimated individuals. So what then would we recommend? So this is your work to rest ratio and then your water intake. So work to rest ratio for unacclimated individuals, we would want 20 minutes of work to 40 minutes of rest. In individuals who have gone through acclimatization, we could have some pretty continuous work here with fluid ingestion for a light intensity. For moderate intensity, that changes. Even if you're acclimated, right, we still want a 30-30 ratio here, and 10-50 if you're unacclimated, okay? If you are engaging in heavy work in that 87 wet bulb globe temperature, and you're not acclimated, we would say avoid work in that case, okay? And increase water intake, right? So these are just some really helpful practical recommendations, and you can use these two figures in conjunction to determine appropriate ingestion. You can also obviously use these equations to help determine appropriate ingestion of fluid. Okay, sorry, I think I lied. I think I said that was the last thing. The last thing is heat illnesses. So I really quickly just want to cover cramp, syncope, heat exhaustion, heat stroke. Your reading covers this pretty clearly, so I'm not going to go over it too much. But cramping, generally, we've got, so it's just muscle spasms happening with slightly increased core temperature. Sometimes with not increased core temperature, it's really individualized. So we actually don't know as much about cramps as it seems like we should. So a lot of times people will say, oh, well, it's because you're dehydrated, or it's because you don't have enough electrolytes. There's actually not great research to support that. Individuals can cramp at any time, whether they're in the heat, whether they're euhydrated or dehydrated. So in any case, some pretty unclear research here. Mechanisms seem to be more neurologic as opposed to physiologic. Syncope is just like a brief fainting episode, might be just severe lightheadedness. With syncope, you typically see decreased heart rate, decreased respiratory rate, pale skin, but no significant increase in core body temperature. With heat exhaustion, we see decreased blood pressure, increased heart rate, increased respiratory rate, pale skin, and an increase in core body temperature beyond that 98.6, which is typical. So just anything above that. And then heat stroke happening above about 104 with disorientation, someone behaving sort of irrationally, definitely some hyperventilation happening here. So this may help you identify these heat illnesses in someone you're working with. And there is a question about that on your post-class engagement as well. So to summarize, right, muscular actions produce heat, skin, blood flow, and sweat dissipate heat. which requires additional cardiac output. Sweat loss does decrease plasma volume. We can see with acclimatization that plasma volume increases. A different time course for each response. So you can go look at those different time courses for increases in sweat rate, right, which didn't really peak till about day 12 versus our heart rate and plasma volume seem to sort of level out around day 6 or 7. Sauna and hot tub do seem to facilitate adaptation. Heat acclimatization does improve even cool weather performance. And then in order to minimize the effects of heat, obviously proper hydration is recommended, pre-cooling and per-cooling as well. And with that hydration, thinking about some of those sodium, potassium, and carbohydrate supplementation with that. Okay, I'm going to give you a little break and we'll move on to talking about altitude.